Hi, I'm Rachel Barkey, and this is my third module. So I'm going to start with multiple regression and correlation. MRC is a measure of association that is typically used for observational studies. It helps define and explain more complex relationships that include multiple variables, as well as helping researchers understand their predictions and where they missed in predictions. It tries to estimate the outcome of interest. So there are many assumptions underlying regression, and before looking at the results, we need to check to see if those assumptions are met. The first diagnostic I ran was checking for bivariate outliers. So this is just an eyeball test. By looking at the scatter plot matrices, I don't see any glaringly obvious outliers. If there were any outliers present, I would need to decide if I leave the outliers in or take them out. According to Cortina, researchers have to be careful when deciding to delete an outlier, as the decision is often made post hoc and is often made because deleting the outlier better supports the theory. Cortina proposed a solution to this by having agreed upon guidelines for dealing with outliers and making sure that there's a sound theoretical basis for making the deletion. So next, I checked for multicollinearity. So you can see from the correlation table that X1 and X5 are not significantly correlated with each other, but that X1 and X6 are. So this violates the assumption of not having multicollinearity. So we also want to look at the variance inflation values. And so the variance inflation values helps if we don't see any significant correlations in these tables. Taking a look at this helps to see if there actually is in fact correlation that is messing with our results. So you want the variance inflation value to be about 1. So X5 is good. However, X1 and X6 have variance inflation factors that are 1.4, which makes sense since those values are since those factors are correlated with each other. So again, this violated the assumption of multicollinearity, and we have to watch out for this in our regression analysis. It probably messes it up a little bit. So another assumption to look at is the assumption of independent residuals. Residuals must not be correlated with each other or with any of the predictors. So to check this assumption, we look at the Durbin-Watson statistic, which should be around 2 if the residuals are independent. In this case, the statistic is 2.1, which is good, so the assumption of independent residuals is met. This slide looks at influential cases by looking at leverage values and Cook's distance. Leverage tells us how far a data point is away from other data points. And Cook's distance tells us similar information. There was no influential cases while looking at Cook's distance. However, when looking at leverage values, there was one influential case. The regression was run with and without this influential value to determine how the value changed the regression results, which I'll discuss later. So another assumption to check is that the average error of the residuals is 0. In this case, it is, so this assumption was not violated. So the graphs on this slide are checking 2 assumptions, homoskedasticity and linearity. The first graph here is checking for homoskedasticity. Homoskedasticity is checking to see if the homogeneity of variance, if there is homogeneity of variance, and making sure that there is equal variance across the data. Heteroskedasticity would be a violation of this assumption. There would not be equal variance, and the data points would split somewhere in the graph. So the other graph is checking for linearity. Linearity is an important assumption to check graphically because MRC assumes rectilinear rather than a curvilinear relationship. And the only way to check for this is by graphing the data points as seen as in Anscombe's data set. So this data does have a rectilinear relationship, so both homoskedasticity and linearity assumptions are met. So the next assumption to check is to see if the distribution of the residuals is normal. For this, I looked at a histogram and a normal PP plot. You want to see if the histogram of the standardized residuals looks normal compared to the normal distribution curve, and in the PP plot you want to see that the data points are lined up along this straight line. They're both close to normal but look a little bit funky, so to put quantitative values on it, I checked the skewness and kurtosis values. So you want the skewness to be around 0. In this case it's 0.24, which is fine. And then kurtosis, you don't want it to be less than -2 or greater than 2. In this case, it's negative 0.7, which is also good. So the assumption of normality is met. An assumption that I didn't check for that I think is important to mention briefly is that MRC also assumes that the prediction of y does not depend on or require other predictors that we did not include, and that we included all of the relevant variables with no error of omission. So once we check all of those assumptions, we can look at the regression results, which, since we did violate multicollinearity, something's probably up. So here are the regression results for Y3 with the predictors X6, X5, and X1. And then this is with the influential data point, and these ones are without the influential data point. So for parameter estimation, we want to look at the B values, and the B values estimate the unique variance among the predictors, and it gives us how much variance is explained by each of the predictors. So when predictors are correlated with each other and there is an interaction, we want to assign variance according to some hierarchy, and this can be done through either type 1, type 2, or type 3 sums of squares. The types of sums of squares used depends on theory. However, as predictors get more independent, the types of sum of squares don't really matter. So these unstandardized B values are in rise over run units, or X over Y units, and the standardized beta coefficients, the standardized B values, don't have any units assigned to them. So a common assumption is that the standardized values in the standardized regression equation is easier to compare to other regression equations than the unstandardized equation due to its lack of units. However, Gary King argues that standardization can actually make it more difficult to interpret, and it does not allow for better comparisons and does not add meaning. He says that standardization makes the results more difficult to interpret, does not add any information that may help compare effects from different explanatory variables, and may actually be misleading and add misleading information due to these reasons. The results should not be standardized automatically, but should be standardized thoughtfully. So here's my unstandardized regression equation, and then here's my standardized equation. So in the standardized equation, the intercept is 0, and the mean of x and y is also 0. So looking over here in the significance column, X1 and X5 are both significant, but again, you have to be careful with X1 since it's correlated with X6. They're both significant at the 0.05 level for predicting Y3, so we can reject the null hypothesis in that case. And the p-value for X6 is 0.96, which is much greater than 0.05, so we fail to reject the null hypothesis. And looking at the R values at the top here, you want the R value to be close to 1, because the closer to 1 the R value is, the closer your data fits the regression equation. So once removing the influential data points, our results change a little bit, as you can see in the differences between these two equations. However, the biggest change happens in the p-value for X5. It goes from 0.004 to 0.01. However, we still have significance at the 0.05 level for X5, but for X5 and X1, but not for X6. So it really didn't change our results that much. All right, so now we are transitioning from MRC into ANOVA. If you want to make this transition mathematically, you can use the point by serial calculation. ANOVA is an analysis of variance. It's a measure of difference. ANOVA is typically used in experimental studies rather than observational studies. And where MRC is looking to see if factors are significantly associated, ANOVA is looking to see if groups are significantly different from each other. You can do this by running an omnibus null hypothesis significance test to see if there are any differences among the groups. So the omnibus test does not tell you the direction of differences, but if there are any differences present. Post hoc analysis, though, can tell you, and I can give you an idea about where the difference is and what direction the differences are coming from. So ANOVA also requires different levels of measurements than MRC. ANOVA uses factors and MRC uses covariates. However, they are both part of the general linear model, and they both focus on understanding variances, offer similar hypothesis tests, and require the Gauss-Markov assumptions. So like in MRC, when running ANOVA, I first checked the assumptions. In ANOVA, the assumptions came down to IID, which stands for independent, identically, and normally distributed errors. In ANOVA, the term error is used rather than residuals in MRC. This comes down to a philosophical difference between the two analyses, MRC assumes that deviations from the mean comes from an incomplete characterization of the model, where ANOVA assumes that deviations from the mean comes from error due to the participants. An important part of ANOVA is that all groups have an equal sample size. This chart shows us that we do. Also, since both variables only have two levels, 0 and 1, post hoc analysis is not needed. So the first assumption from IID that I checked was that errors are identically distributed or homogeneous. This is done by looking at Levene's test for equality of error variance. In this case, equality of error variance is not significant at the 0.05 level, showing that errors are equally distributed and that the assumption is met. So this graph is checking for the independent errors assumption. You want the observed and predicted values to not be parallel. You want them to be overlapping and sort of grouped together. You don't see this in this chart, so the assumption is violated. The last assumption to check is that the distribution of errors is normal. You can also check to see the independent or the homogeneity of errors here too by looking at the distribution. So looking at the standardized residuals, you can see that the values are evenly distributed. It's a pretty normal distribution, so it meets that assumption. Now looking at our ANOVA results, the F-test gives us our parameter estimates and tells us how much variance is explained by each factor. In this case, our F values are small and do not explain much of the variance. So you can see that in the total sum of squares column, our interactions and our main effects only take up really small numbers here. And then when we look at our error value, it takes up 68 of the 71 of our total sum of squares. So it makes sense that when we look for significance, we don't see any significance at the 0.05 level. So for all of the cases, we fail to reject the null hypothesis. It also makes sense that we didn't find any significance since one of our IID assumptions was violated. So that was regression and ANOVA. Here are my hand calculations, and that's it. Thank you.